Good morning. We hope you had a great time last night. I know I did, and hope many of you did. We're a little more sparse this morning. I think a few folks maybe stayed out a little too late, which isn't all bad, but they're going to miss something great. This morning, we have an opportunity to hear from Purdue. Specifically, we're going to hear from Preston Smith, the manager of research support services at Purdue, and they're going to tell us an interesting story. Like many of you, they are Moab users. But unlike many of you, they've only been Moab users for maybe a couple of months. And Preston's going to talk to us about why they moved to Moab, kind of where they're coming from. They were PBS Pro users, and why they switched over to Moab, and kind of where they hope to go with this. So I think it'll be an exciting topic, an exciting discussion. And with that, let's give Preston a big hand.
All right, thank you. All right, thank you very much, everybody. Like I said, my name is Preston Smith. I'm the manager of research support for Purdue's Rosen Center for Advanced Computing. So to clarify the timeline a little bit, we've been a Moab job for approximately 2 weeks now. So at this point, we really have nothing but good things to say about it. So I'm sure you guys from Adaptive are excited to hear that. On the other hand, if you're looking for deep technical wisdom on all the crazy things we've been able to do, this probably is not going to be the talk. Instead, what I'm going to use this time for is to give you a little bit of a background on HPC at Purdue, where we've come from, how our business model works, our community cluster program, and how we plan to use Moab in the future to make our faculty more productive. All right, so just a little bit about who we are. I work for a unit in Purdue called the Rosen Center for Advanced Computing. I manage the research support team, so we work with the faculty at Purdue to effectively use their HPC. We provide the incident response when they have problems, help them make their code more efficient, use the machines more effectively, set user policies, and that sort of stuff. The Rosen Center is a unit of what we call ITAP, the Information Technology at Purdue. It's the central IT organization at Purdue. So rather than being a separate entity, I know some of our peer institutions are organized differently. The University of Texas and TAC and NCSA, their supercomputing centers, while affiliated with the university in some form, are a distinct entity. Whereas we, and I think IU probably is the same way, are a unit of the central IT organization. So eventually we report to the CIO. We're kind of in the same organization as the folks that run SAP, for example. So the Rosen Center provides advanced computational resources and services to support our faculty. We also are involved in research projects of our own, building experimental resources and providing new capabilities to these same researchers. So we've actually done computing at Purdue for a long time. So I'm going to kind of give a little overview of computing at Purdue through the years. In 1962, Purdue actually founded one of the first actually computer science department in the country. With 5 faculty back there in 1962, and it's grown quite a bit. I don't remember the enrollment these days, but it's a lot larger than five faculty and probably 10 students. In 1985, we're the second EDU domain on the internet with a couple other notable players there. And today, our faculty do a number of different programs in computational science. There's the obvious ones: computer science, computer engineering. We have a College of Technology, which has computer information technology, which are much more like applied engineering. The students in the technology programs get a lot of the same type of skills that computer engineers do, but it's a lot more hands-on. These are the students that actually pick up soldering irons instead of doing it all in MATLAB. And then in recent years, we've spun up a number of interdisciplinary computational science programs. So our physics students have entire subcurriculums in using computation for their research, similarly with atmospheric science, chemistry, et cetera, and so on. So in the early days, in the late 60s, Purdue became one of the first academic institutions with a supercomputer. We had a CDC 6500. I'm sure I'll see some nods out here. People may recognize some of these machines. In the 1980s, Purdue acquired a Cyber 205. And the Cyber 205 is one of the first machines that we had where we got involved in writing our own software to manage the job submissions. In the 80s, we had a number of machines in the Cyber 205 series, including an ETA 10, which was running System 5 Unix. By the time we get into the 90s, Purdue operated an Intel Paragon. The Paragon was scheduled with NQF, so I'm sure there's folks that may have used that before. Staff at Purdue, again, wrote extensions to the software, wrote our own scheduler called NCSS, and there's a little link to describe what that used to do. And it was written to allow fair share to be implemented in NQS, which I understand was perhaps not possible in the default configuration. By the time we got into the 90s, we're getting into some more recognizable stuff. There was a cluster of standalone IBM RS6000s that we ran, and then in 1995 acquired an IBM SP2. By this point, all of these resources are running PBS Pro as a resource manager, and they continued to use the locally developed NCSS as a scheduler. By the time we get into the 2000s, we're getting into the Linux cluster era. The first Linux cluster that we operated at Purdue was what we called a recycled cluster. We would take these retired lab machines out of the student labs where the students would sit down and use their word processor and surf the internet, and we would turn them into compute nodes for a year or two after they've reached their end of life in the labs. It was used with PBS Pro. NCSS was the scheduler, the idea being that we wanted to keep this environment as close to the IBM SP as possible. Because many of the faculty that were trying out this newfangled Linux cluster thing were already coming from the SP. One other effort that we've been involved with for many years at Purdue is what we call now DiaGrid. This is a campus grid. It's a high throughput computing resource that we use the Condor software to make a freely available resource for our researchers. So all of our clusters we primarily schedule with PBS. We run Condor on those same nodes, and PBS and Condor can communicate to each other. PBS is not running a job. Condor is free to schedule on it. And by doing this, we can create a fairly substantial campus grid that's available to anybody on campus. So you don't have to write an allocation. You don't have to pay in any money. It's just something that anybody can use. And it's actually a fairly capable resource on existing hardware that we already have paid for, that we're already paying for staff to manage, power to run, software to operate. It can provide us, and it has the last couple of years, 18 million hours of computation for varying degrees of no additional cost. The problem with a resource like this is it's very limited in the type of work that you can run. We definitely couldn't run the type of work that you would run on a Cray, on a Condor pool. But if you're running lots of single processor jobs, like a parameter sweep, Condor pool has turned out to be very effective for our faculty. So by about the mid-2000s, this is kind of what our environment looked like. We had a number of unique compute resources, all separate, running various combinations of resource managers. Some of the older systems, the SP, the recycled clusters, and a couple of Sun clusters, were running PBS Pros as the batch system and using NCSS. At this point, we'd started up our community cluster program, which I'll talk about here in a minute, and it was running PBS Pro and over the years, various combinations of MAUI and then later Moab. A couple resources ran PBS Pro exclusively on SGI Altix, and our community clusters eventually after we'd given up on Moab the first time. And then we had Torque and MAUI on a small cluster, Slurm on our Cortex system, and then the Condor grid. So now we're looking at the situation about 2003, considering what we can do. We have faculty who have computational needs, and how can we go about providing this? By this point, the IBM SP that the university paid for out of central funds was 7 years old, which that's getting a little long in the tooth. Like I said earlier, the Condor pool is very effective. It delivers lots of hours, but it's for one very narrow type of work. It doesn't help everybody. We have an inexhaustible supply of PCs to turn into recycled clusters, but there's a couple problems with that. These PCs may not be designed for HPC. They're desktop machines. And frankly, they're already 3 years old at the end of their life cycle by the time they even become a compute node. The faculty could go out and buy something on one day, and it's already much more capable than what we would provide them in these recycled clusters. And the bottom line, at that point in time, the university was not inclined to make a large capital purchase to build a general purpose supercomputer system that any of the faculty could just use. So this brings us to our community cluster program, and this is kind of the main subject of my talk today. The community cluster program is our business model for how we provide HPC. I heard several talks this week about how their university allocates time to their faculty members. The Indiana folks said that Any of the faculty are free to use their Big Red system. That's one of their draws to bring faculty in. I think the fellow from Michigan was saying that they have an allocation process. The community cluster program is neither of those. You get what you pay for. So our first draft of the community cluster started in about 2005, 2004. And these are the little background on that. So like I said, with having these recycled clusters and already using out-of-date hardware, we just really can't provide cutting-edge capability. At that point in time, as a result, faculty members were writing grants. They were getting the departments to give them startup funds to build a small cluster in their lab to get their work done because it wasn't available to them centrally. So the solution that we came up with, and many other sites have done this as well, is to pool these funds to operate these clusters on the researcher's behalf. So the faculty no longer have to sacrifice a grad student or themselves from actually doing what they're paying them to do and to manage a cluster. Here's a testimonial from one of our electrical and computer engineering faculty members who said exactly this. He actually converted to the community clusters recently. He ran what at the time, I think it was a 2006 era cluster that was about 200 nodes, and it was sitting in his lab, taking up space. When it actually worked and he was able to do stuff on it, I can only imagine that it was noisy and his grad students hated sitting next to it. So as a way of doing some cost saving at Purdue, we're doing a data center consolidation program. So the university administration will gladly take these old clusters out of faculty members' labs. In exchange, they wind up in the community clusters. And they often find that it's an effective way to get their computation done while freeing up their grad students, and like Professor Sudoff says, gets them out of the computer maintenance business. So our first draft of the community cluster program had some basic rules, and these are pretty much in common to any community or condo cluster that people may have talked about. Rule number one, you get out at least what you put in. Whether you're a small faculty member from liberal arts that can buy one node, or you're a very important computational faculty member from electrical engineering who can buy 100 node, you get set up with a queue that guarantees you access to at least that many CPUs. So if I have one on 8-core node, I can run 8 cores worth of work, and likewise, if I have 100 or 1,000 nodes, I get that many cores. The faculty member students are set up with access to that queue, and nobody else. The nodes don't actually map, the queues don't actually map to a specific node. So the faculty member won't go through and say, that's my node right there on slot 4 in rack 3. It's just much more of a share basis. But wait, there's more. What if your neighbor isn't using his queue? He's like the electrical engineering faculty member may see the fellow from liberal arts and says, you know, he never uses that node. It's a shame that it sits there and idle. So we set up a method for faculty to use each other's nodes. You can use it if they're not, but the rule is that you might be preempted if he comes there and wants to use it. And the faculty think, okay, this is great, this seems reasonable, I can run that risk. And most importantly, you, the faculty member, don't have to do the work, or your grad student don't have to do the work, honestly, nor do you have to provide the space in your lab. ITAP, it's our organization, provides the data center space, so it's a real data center, not just your lab. Professional system administration staff, application support staff, performance engineering, networking, all that good stuff. All you have to do is submit jobs and get science done, get your tenure, make publications. So this model worked well, mostly. Not quite everything worked out well. There were some issues with this that made it a little hard. The acquisition of the clusters was fairly ad hoc. We may have a couple different rounds of purchasing of one cluster, which would result in heterogeneous clusters. Some of these early clusters had mixtures of 2 or 3 different processor types, different interconnects. Most of the cluster might be giggy, but these 2 racks are InfiniBand. And I'm sure most of you that are system ins out here will nod, knowing that it's just hard to deal with. Most importantly, the opportunistic use of others' nodes by a preemptible queue was a great theory, but in practice, it really didn't work very well. The preemption was unreliable. When you'd get preempted was unpredictable, which made for grouchy faculty members. I should have used the Angry Bird graphic that was in one of the talks yesterday, because I've definitely seen that face. And then also kind of the converse of the ad hoc acquisition, if the faculty member didn't have funds right when the purchase was being made, then he missed out. Just, if my grant came in 2 months later, I could have gotten into the community cluster. So as a result of this, community clusters of only 1 or 2 communities began to sprout up, and we ran, I think, about three or four of those at one point. And with that, then the economy of scale is lost. You lose the big price break you get from buying all of these nodes at once. The faculty then don't have anybody else's nodes to borrow from, so that a lot of the selling points are lost. For our business folks and the people that run the data centers, the early agreements in the first draft of these community clusters had the problem where there was no end. Okay, great, we buy these nodes, the faculty run them, these are the rules for when we run them. Overlooked was the clause where this agreement ends on this date, and this is what happens to the nodes. So you can imagine the faculty members say, hey, I've got nodes, I'm going to run on these things until they turn into dust. Whereas those of us in IT said, God, those things are old, let's get them out of here and get something more capable in. So that was a minor oversight. By the time the community cluster program started up, we were still running our locally developed, at that point, 15-year-old NCSS software, even though by at this point, its authors had long since left Purdue, and nobody was able to maintain and understand the software. So with the community clusters, we began from the ground up using Maui as the resource manager, or as the scheduler to manage the jobs, with PBS Pro as the resource manager. Maui had some issues. It may not have been the most scalable thing to run on some of these larger systems at the time. So after some struggling with Maui, we decided we were going to convert to Moab, pay the money, and see what that worked, how that worked out. And in the end, that didn't even work out well. We ran PBS Pro as the batch system, and those of you who have probably worked with software that comes from 2 different sources, nobody quite was sure where the incompatibility lied. So we wound up just going with PBS Pro as the resource manager and the scheduler, and operated in that way for the next period of time. So with that, our version 2 of the community cluster program, we decided we were going to refine some of the ground rules a little bit. The most important thing is that the clusters are going to operate on a 5-year life cycle. The idea, every year around springtime, we'll send out a notice, hey, we're building a cluster, bring your money, come to this informational meeting. We're going to build a new cluster for the faculty every year. They can just count on that, they can write their grants, being aware of that cycle, and not have to worry about missing out on when the next cluster is going to come. With having this 5-year life cycle for the cluster, one thing we asked all the vendors that would bid on the clusters is that, hey, you have to provide us a 5-year warranty. So while these machines are on, we need to have support for the hardware, and they all, fortunately, were willing to do that. But most importantly, after 5 years, the MOU with the faculty member says the cluster will be retired. We will shut these things off, they will go to salvage, they will be sold to some third world country, something. They will not stay here and run into perpetuity. At the end of those 5 years, though, the faculty will get some sort of a credit on the residual value of their nodes towards the next cluster. So if I'm a faculty member that doesn't have tons of money, if I'm a liberal arts guy and I have 2 nodes, I may get something back, a credit that's maybe half of a node towards the next cluster that comes on to replace it, and I only have to come up with maybe $1,000 to continue on having access to a high-performance computing resource. And then from the funding side, the community clusters now appear to the faculty as paying for a service. I mentioned earlier that the faculty are not purchasing this exact node in Rack 2 slot 4. They're getting access to 4 shares, for example. I was actually amazed that the funding agencies liked this. They didn't seem to have any heartburn on that. It looks like you're paying for a service, not a capital purchase, so the faculty don't wind up not having to pay overhead on this as well, so everybody's happy about it. Operationally, the preemption idea goes away. Like I said, it was a good theory, but didn't really work out. We replaced the idea of preemption with what we've called a standby queue. You can run all the jobs that you want on your neighbor and your friend's nodes beyond what your queue would let you, but the drawback is you're subject to a 4-hour time limit. So this actually worked out really well for everybody involved. The faculty members whose nodes are being borrowed know that at the worst, if I submit a job that wants to use all my nodes, I might have to wait a couple of hours because somebody's mooching them. And the faculty members that are using the standby queue know my job is going to finish. I don't have to worry about it being preempted 98% of the way through and having to start back over. I just know that I can only run stuff in here that'll fit in the time limit. So everybody wound up being happy with that model. We also further refined what is centrally funded and what exactly the faculty are paying for. So Purdue clarified that all of the central things we fund. The data center space, the storage, each cluster gets a centrally funded Lustre file system so that they can actually put their data somewhere. The networking support, software admins, using the university's central accounting system, a process for handling user support using the university's ticketing system, and the faculty, all you have to pay for is the nodes. Now, for selecting the machines, the process developed that we would send out an RFP to all the interested vendors, kind of a general RFP. Like basically, we want a cluster that can do some vague criteria depending on who's expressed interest. Depending on which cluster we have, we may have a heavy investment from high energy physics, which they don't care about the interconnect. They just want lots of cores that they can run loosely coupled jobs. But then the follow-on cluster is heavily used by the Earth Atmospheric Science Department, doing climate models and people doing CFD, and they would want much different type of nodes. So a survey would be sent out to the faculty to see who wants to buy, and those would help craft the requirements for the RFP. So when the RFP comes back in, we get what the vendors have proposed for us, we get some evaluation hardware and turn the faculty loose on them to benchmark, see how they work with their codes. With the RFP, the vendors were also asked to give us a 6-month or so price protection on the nodes, so that the faculty who maybe didn't buy in on day one and they come around 2 months later and said, oh, I'd really like to get some of those nodes, we can still get them. We can still get them at the good price that we've negotiated, and the faculty just pay later. And the cluster grows slowly over time. As a side benefit to the rest of the university, they get to benefit from our price break. So everybody in various other IT units can buy 1U servers and get the discounted price. Then after the faculty have benchmarked and looked at all the hardware, we'd get them in a meeting and make the selection of which bid we're going to select. And in actuality, that usually worked out as which one is cheapest per core. So a lot of effort for for going with the cheapest one. So our first cluster in this refined model is what we call steel. Cost savings from power and cooling for our first round of clusters, Hamlet, Lear, and Macbeth, were substantial enough that we could take a 512 node, 2 CPU, 2 core, so only 2 CPUs per node cluster that took up an entire room. We could take that cluster, consolidate it down into 2 racks in steel, and still come out ahead. So all of these existing Generation 1 clusters were retired, and all of the owners were moved into this new system, Steel. Steel was set up in a day. This was a little stunt IT, where partners and IT staff from all over campus, so the people that bought into the clusters and their students and their IT folks joined together, and we unpacked, installed, and started a Steel cluster into production one day. This made all the faculty very happy, and they were running jobs that afternoon. You know, those of you who've had to burn in clusters before probably know what's wrong with this, and we know this too. But it was certainly a fun experience for the campus to see happen. So here's the overview of what type of scale we're looking at today on this community cluster program. Steel, the first cluster that we ran, is a Dell Intel GigE cluster with 7,000-ish cores. And you can see the breakdown of the number of faculty and the number of departments that each of these clusters is reaching. So every time we do one of these new clusters, I don't know where the button is here. Oh, there it is. Going chronologically that way. So the Codes cluster came second, Rossman third, then Hansen and Carter. The clusters get a little bigger. They get a little more capable. We go from a GigE cluster, wound up with 3 10 GigE clusters, which was an improvement over GigE, but you know, I bet there's not very many other people running 10 GigE clusters out here. And then finally, the Carter cluster, which we just brought into production a couple weeks ago. This cluster is a very high quality HP cluster. So one of our HP folks are still here. I feel like I'm doing a commercial for them with the sign up next to me. With Intel Sandy Ridge processors and FDR InfiniBand. And Carter is the first one that we've gone back to using Torque and Moab to manage the cluster. That's where we are today. So with version 2, we've fixed a lot of the business process issues. That's much more manageable now. We can execute agreements and everybody's happy with them, and that works out. But there's still some issues on the operational side. PBS has some problems that bother us. As we reach larger scale, limitations like PBS Pro's use of RPP on the nodes provides issues. If RPP can't be reliable, it will drop jobs on the floor, make them requeue, and again that makes the Angry Birds face show up in my door. There's bugs with exclusive access, scalability on large clusters where PBS Pro would just frankly hang. One issue is that we could also not fair share on a single queue. So one of our large customers on Steel is the TerraGrid project now Seed. And they make heavy use of the standby queue where they can run extra jobs beyond their share in 4 hours. The problem with that is the queue stuffers can come in there, fill the thing up, and PBS Pro can only do them in FIFO. So the people who are way down in the queue have to wait and wait and wait. And there's no way within PBS Pro to fair share only within that queue. If we want to fair share, we have to fair share across the entire cluster. And I don't really necessarily want the faculty's use of their owner queue to affect their use of the standby queue. So we're just kind of stuck at that point. One thing that bothers our management is having to take unnecessary downtimes. If we need to push out an update to PBS, we have to stop the entire cluster in order to update it. The scheduler, the MOM, and all the various pieces of PBS Pro all have to go in lockstep. We can't do something like we can with Moab, where we just update Moab and everything keeps going. Occasionally we want to implement policies with the user's jobs after the fact. PBS Pro has a concept of hooks, which is there's a loosely documented Python API in the server where you can take the submission and do things with it, like changing the wall time or any other attributes like that. It's pretty comparable to the submit filter that we have with Torque, but much less easy to use. And then more from the process side, we wanted to set out to eliminate the non-value-added processes. The users were forced to send tickets all the time just to add a user to their queue, to get a quota request that we always say yes to. So we did set out pretty quickly to do a few things here to take us out of those non-value-added things. We provide a portal to our faculty to look at how their queue is being used, how many hours am I getting versus how many I'm paying for, which of my students are using the cluster most heavily, and give them an interface to manage the queue directly. If I have my new student that just signed up, I will just go there, type their name in, enable them on the queue, their account gets created, and off they go. These interfaces here, actually, they've only been in production for a couple of months, and this has turned out to be quite a selling point for the community clusters. One new faculty member that came in was looking to buy nodes and saw things like this and decided, okay, these are value-added things. These empower me to get stuff done, and that helped sell him into the clusters. So the impact of these community clusters. How do we measure if this is even a successful program or not? Would we be better off just not doing HPC? That's probably a bad idea, at least in this crowd. Or the university just centrally funding a machine and letting everybody onto it. So this table illustrates the number of cores in all these clusters spread out among the various departments. Some of the ones here at the top are the ones you would certainly expect to be heavy users of any cluster, and Purdue is no different. One of the things that entertains us the most are some of these people down here at the bottom. Our management school is getting more into HPC, landscape architecture and horticulture. A communication faculty even bought some nodes. He's doing an interesting study on analyzing all the data in Wikipedia for analyzing the relationships between submitters. So it's great finding new customers for HPC with just really minimal investment. Even a I don't want to say even a communication faculty, you know, they don't have the access to equipment funds the way an engineering or physics faculty member might. But for a small investment of just a couple $1,000s, they can get access to resources that their colleagues just have no option for. One of the interesting things that we've analyzed with our community cluster partners here is how these particular users tie into the university's total research funding. So the top of the yellow bar here is the total funding, external funding brought in by the university, and the white part is the portion of those who are community cluster owners. So in 2011, 48%, I believe, of the university's sponsored dollars were brought in by HPC users. So I think that's a pretty good indication of what our cutting edge faculty are doing and how they need HPC to get their work done. Here's the obligatory getting larger to the right graph that shows the growth in usage over time. 128% increase for 2011 and an 18% increase in number of research groups. A research group is a faculty member and has associated students, so 18% more than we had the previous year with that cluster. And then finally, the capabilities provided by the community cluster have gone up. As the program has matured, as you saw in the table about the clusters, from our Gigi cluster steel to what we have today in Carter with modern processors and the fast interconnect, the capability and the size of the jobs the faculty are able to do have gone up. But most importantly to university administrators in today's economic climate is the cost effectiveness. Is this an effective way to provide HPC? And we think it is. Every time we've done one of these clusters and negotiated with the vendors and found ways to leverage existing hardware or staff, we've been able to get the cost per gigaflop in the cluster down every time. Steel started up with $27 per gigaflop, down to just over $10 per gigaflop on the cluster on Carter. To kind of relate to the cloud computing model, where you pay by the core hour, our community clusters work out to be fairly favorable. This is a fully loaded cost. This includes power, facilities, all the admin stuff needed to run the cluster. And when you divide out the number of cores, the number of hours in a year, it costs just a little over 2 cents, and then Carter gets closer to like 3 cents per core hour. The Ranger machine at TAC, there was a study published what their per core hour cost is, and then the Amazon price is obviously published as well. So now we're getting to the Carter cluster, which we just brought into production. Carter gives us some new capabilities, and it honestly came together differently than all of our other systems. I described the process earlier where we would collect requirements, send out a bid, sort through them, and then buy the cheapest. Carter was actually worked out to be brought together differently. Many of you will probably say, yeah, this looks like how everybody else procures a system. We worked with HP, Intel, and Mellanox to build a Sandy Bridge and FDR InfiniBand InfiniBand cluster well before they were available. With the system integrated at once versus instead of over 6 months, every time somebody buys a node, we rack it up and the cluster gets bigger by a node, and not going into production on day one like we did with steel. We were able to do much nicer things, burn the cluster in, get any integration hiccups or firmware problems worked out. So that worked out well as well. And with the nodes all on hand and running, we can get the faculty on the entire system to test and then immediately turn around and sell them access to the nodes, instead of having to extrapolate how their code works on the one eval version of Dell's piece of hardware. They can run at scale on Carter and get a much more realistic picture. And then one of our faculty members already had some good success by testing his code on Carter, and seems to be very happy with that. But what about Moab? We still haven't talked about that. And yes, I know I promised to talk about that at some point, and I believe we're at that point. So during Carter's pre-production phase, we worked with a group of about 15 to 20 users to give access to the system, to benchmark and evaluate things. particularly for performance and getting their code working, but also to test out the use of Torque and Moab as the batch system for the cluster. A couple things we wanted to figure out on this. Does Moab solve these schedule-related issues that we've seen? And more importantly, are the users able to adapt to little differences like QSub being subtly different, with maybe some options not being there, and Moab commands like check job and stuff that they may not have seen before. So in the end, the evaluation turned out positive. Carter went production with Torque and Moab about 2 weeks ago, and we identified a lot of things that in the end are going to help our faculty's productivity. There's no more RPP. We disabled RPP and used TCP, and its associated issues related to it not actually being an R, being reliable. We're now able to span queues across node types, which PBS Pro would not let us do, at least how we had it set up. The health check script was a very attractive feature, and we do have some basic health checks put in there. Check for the luster file system is there, full file system, that sort of stuff. It's already, in 2 weeks, has saved several faculty members bacon from dropping jobs on the floor, so that's already a bonus. We do have GPU support. The Carter cluster has some GPU nodes, and we like that the Torque has the ability to actually manage them. Most importantly for our management is that we can push out upgrades without having to idle out and stop the entire cluster for a day. If we need to just update Torque, I understand we can just push out a rolling upgrade and go. If we need to get better scheduling capabilities with a new version of Moab, it's great to us that it's decoupled and we can just stop Moab, put in the new version of Moab, and start it back up again without having to drop everybody else's jobs. That's a huge win. That alone made my executive director happy enough to write the check. Our newer clusters, the Hanson cluster, for example, is a 48-core, 4-socket Opteron system, and actually having the ability for Torque to know about the NUMA and CPU sets on the machine is a win. We had a number of faculty that were struggling with getting predictable performance on this machine, just because their job would run on one NUMA node and the memory would be over on the other NUMA node, and trying to predict how it was going to work. They were even doing silly things like using NUMA CTL to start the job and assign it to a processor manually without the back system helping them. So if we can help them, then this is a win for us as well. And we can do fair share within a queue. This is going to be a good one for us. The Steel cluster is going to be one of our next machines that we convert to Moab, and getting this capability for our Exceed customers is going to be something that will make both them and us happy. And then finally, the submit filters are a dramatic improvement over PBS Pro's job hooks function. We've already found a couple of administrative policies that we can either say, no, don't do that, that won't work like you expect, or insert things into submit file into user submissions, and it's much easier. So future directions, we've got one cluster up. We're going to convert others. What else do we want to do with this new partnership with adaptive computing and using Moab, and how can Moab help us with that? So the one thing that we always want to do is provide new capabilities for our faculty members. Our management has asked us to come up with tools to provide job status monitoring, being able to tie submissions into GUI applications, maybe just do a web service call to get the job in there. So we've started looking at the Viewpoint software a little bit, and we're eagerly looking forward to that package maturing a little bit and seeing if that can help us and help us deliver some of these types of things. We're hoping to take advantage of Moab's integration with license managed software. MATLAB at an engineering college is a very popular thing, and contention for licenses is always an issue. We're very excited to be able to use that. I think somebody was saying yesterday that we can actually fair share on the number of MATLAB licenses, which seems like a real win. So when somebody comes in and uses all the parallel MATLAB licenses, we can keep them from doing so. One of our immediate term projects is we're going to have to develop a Rosetta Stone for PBS Pro to Torque and Moab as we migrate our existing clusters. For example, a user with PBS Pro will use syntax like -l select =2 and prox =16, Whereas in Torque, no, you need to do it the older way that you used to be able to do in PBS Pro. So we either need to document that or have the submit filter helpfully fix that for them. There's a couple other things. One of our recent users on Carter discovered that his scripts that use QStat -W, which puts a wide format on all of the outputting QStat, doesn't actually exist in Torque. So I think we'll try to point in the check job as a way to find that. So we need to just complete a table here of finding all of the things that these users are going to find. We learned yesterday about the Werewolf Health Check framework, and I sent that back to people who were back in West Lafayette, and one of our coworkers was like, "Oh, great, we'll install that today." So I think that'll be a big win for us. And then finally, just in general usability enhancements. I think we can use the submit filter to make QSub be able to tell, hey, there's a scheduled downtime a week from now. Your job isn't going to run past. We'll run past that. Do you really want to submit that? That's frequently a source of confusion. As we know, users may not read the notifications we send them about a downtime, but if QSub is telling them, no, there's a downtime coming up, I think that'll make everybody happy. And then finally, the ability to schedule our GPUs. There's a number of faculty that want to get into that space, and Torque and Moab we see is a great way to help with that. So that's all I have. I'd like to thank everybody for all their help with getting us started, particularly Jess Arrington for helping us through the maze of working with our purchasing folks, and Nick for providing support as we got Torque and Moab up and running. And thanks for the great conference. It's been great for us as new Moab customers to learn all what you all are doing with the software. So thank you.